Let's talk about differentials. What are differentials? Differentials, put quite simply, are just an equation that have derivatives in it. Okay, so if we think about differentials, that now becomes a very, very broad topic. It can encompass a lot of different types of equations. There's entire courses in universities that are taught just on differential equations, and they're just one piece of calculus and or physics, depending on what you're looking at. Two common forms of differentials are usually in form of what's called explicit form and implicit form. So on my screen here, just looking at explicit form, explicit just basically means that it's in terms of one variable. So here we're just looking at a derivative, dy over dx, or the change in y over the change of x, is equal to x squared minus 2x. That would be an example of an explicit differential. Where in the second one, we're looking at an implicit differential. So we still have the change in y over the change of x, but it's now in terms of two variables. It's got x's and y's in the derivative. Today, we're just going to look at an explicit example. And I wanted to come up with a real-world example or something we can imagine doing. When I was a kid, I found out that my dad was drafted into the NFL. So I became obsessed with the NFL and everything that encompassed the NFL. So let's just imagine for a second that we win a contest with our favorite NFL quarterback. So we're going to get to spend the day with this quarterback. So we go to the sports facility, and we've been taking calculus, or we've been taking a physics class, and we're kind of interested to see what this quarterback has in his arm. So we pose a challenge to the quarterback, and we want to see how high can you throw a football? How high can you throw a football vertically straight up in the air? So to do that, we have to look at a couple of things. We've got three things going on at the same time. So let's look at the three different functions we're going to be trying to find. The position function we're going to call s of t. This measures the height of the football at any time. The velocity function is the derivative of the position function. So it's the derivative of s with respect to t, which we're just going to call v of t. And then we've got acceleration. Acceleration is the second derivative of position and the first derivative of velocity, which would give us the actual acceleration of the football. We need some initial conditions. We need to talk about what's going to happen. So our favorite NFL quarterback holds the football, and we know that Earth's gravitational pull is going to be fighting against this football at 32 feet per second, or negative 32 feet per second squared. The initial velocity, most NFL quarterbacks can throw between 50 and 60 miles per hour. All right, so we're assuming since he's throwing it straight up and not forward that it's going to be a little bit slower. So even if you threw it at 51 miles an hour, we're going to convert that to feet per second, and we're going to say that his initial velocity throwing that football straight up is 75 feet per second. And then lastly is the initial position. So we've measured that when he lets the football go, that his hand of the football is exactly 8 feet above the ground. Okay, so let's start with what we do have. We know Earth's gravitational pull. And we're going to take this differential and we're going to solve it. When we talk about solving differentials, really what we're trying to do is we're going to use anti-differentiation to work backwards to find the formulas before them. So we're going to start with the acceleration, and we're going to use anti-differentiation of the differential to get back to a velocity function so that we can figure out exactly how fast that ball is traveling at any time. And then we're going to work that one backwards using anti-differentiation to find the position or the height of the ball at any time. So if we begin with Earth's gravitational pull of negative 32 feet per second squared, and we said earlier that this is the rate of change of velocity. It's the derivative of velocity. So to undo the rate of change of velocity, or to undo the acceleration function, we're going to integrate this equation. So we're going to take an integral of the derivative of velocity. So this gets us back to what would be the velocity function, v of t. So if we integrate negative 32, which is a constant, we know that's going to integrate to a linear term. So it's going to become negative 32 t plus c. Now this c is what's called the constant of integration. The constant of integration is a value that may have been there in the velocity function. So if we think about it, just work the problem in reverse again. If we took the derivative of velocity, we should get the acceleration function. So if we take the derivative of negative 32t, we would get negative 32. If we took the derivative of this constant of integration, a derivative of a constant is 0, so it would go away. So we have to take advantage of the fact that there may have actually been some kind of constant here when we integrate acceleration. So if we think about our problem in our initial condition, we remember that when he threw the ball, so at time 0, that ball was traveling at 75 feet per second. So we can use this as an ordered pair to figure out what the constant of integration is. So if I substitute 75 into the velocity, and we know that it is at time 0, then we see that the negative 32 times 0 is going to cancel out, and we're going to have the constant of integration is just 75. So then we can substitute in this 75 into the c of our velocity function. So now we have the velocity function to be v of t is equal to negative 32t plus 75. So now we know that we can find out exactly how fast our favorite NFL quarterback, the football, is traveling in the air at any time. So if I plug in 1 second, I can figure out exactly how fast that ball is traveling. Plug in 2 seconds, exactly what the velocity is. Now notice that because we have a negative 32, the velocity may be positive or the velocity may be negative. Remember, when velocity is positive, it means that it's moving in an upward direction in this particular problem. And if the velocity were negative, it means that the ball is actually coming back down to the earth at that time. Okay, so if we want to get back to the position or being able to figure out exactly how high the football is in the air at any time, then we're going to have to integrate this differential. So if we look at velocity, which we know is the derivative of position, so this would be ds of dt. So if we take the integral of the rate of change of position, or the integral of velocity, we're going to get back to the position function s of t. So s of t is now the integral of the velocity function. So if we use anti-differentiation, so we're going to integrate negative 32t, we would add 1 to the understood exponent of 1, which would give us 2, and divide. That would give us negative 16t squared. Then the integral of 75 would be 75t. And again, we have a constant of integration that we're going to have to figure out. So we're going to go back to our initial condition. We remembered that the football left the quarterback's hand at 8 feet at time 0. So when we started the problem, the football was 8 feet off the ground. So we can use, again, that same ordered pair, s of 0 is equal to 8, to substitute 8 into s of t, and then we're going to substitute 0 seconds into our times, and this will help us figure out the unknown of the constant of integration. So negative 16 times 0 squared and 75 times 0 are both going to become 0. And we realize that the constant of integration is going to be that initial height of 8 feet. So we're going to substitute this 8 feet into our constant of integration, giving us a position equation, which is negative 16t squared plus 75t plus 8. So what have we actually figured out with our NFL quarterback? We know that Earth's gravitational pull is going to be pulling the ball back to the earth the entire time as soon as it leaves his hand to when it comes back down to the ground. And we know that Earth's gravitational pull pulls the ball back to the ground at negative 32 feet per second per second. All right, so we integrated the acceleration formula, or we used anti-differentiation from this differential to get us back to this function of negative 32t plus 75. So this particular equation will give us the exact speed or rate of change of the football at any time. And it may be positive, it may be negative, depending on whether the ball is still traveling up or whether it's traveling down. Then we integrated, or did the anti-differentiation of this differential of velocity to get us back to the position function. And we got negative 16t squared plus 75t plus 8. So then this equation now can tell us exactly where the ball is above the ground. So depending on the time that we substitute into the t variable will tell us how high the ball is, or the height of the ball at that time. We know that differentials are a very broad topic. Two popular types of differentials are explicit and implicit. There's also many other types. We looked at an implicit differential today, and we talked about solving differentials. And when we talk about solving differentials, if a differential is simply an equation with a derivative, then solving it would be working it backwards or using anti-differentiation or integration to find out what the original function was. So we can take, in this particular problem, a real-world example and find all kinds of information and data of this football that our favorite NFL quarterback threw.